Welcome to Prospective Doctors MCAT Podcast, brought to you by Med School Coach. Each week, Sam breaks down the highest yield MCAT topics so you can score as high as possible on test day.
Hello and welcome to Prospective Doctors MCAT Basics with your host Sam Smith. The goal of this podcast is to cover the highest yield topics on the MCAT and provide you with some sort of insight into the questions that the MCAT really likes to ask. This podcast is going to cover fluids, and I already did a podcast where I talked a bit about fluids, and I did that in terms of the cardiovascular system. But in that podcast, I was really talking about fluids in motion, or what we like to call fluid dynamics. And in that podcast, I talked quite a bit about the continuity equation, Bernoulli's equation, and some other concepts like that. This podcast is going to talk more about fluids at rest, or statics. And it's broken down into two main sections. So first, I'm going to talk about some of the different properties of fluids. That's going to be things like surface tension, the difference between adsorption and absorption, vapor pressure, and then I'll talk about Henry's law. And then I'll dive more into these fluid statics concepts. I'll talk about osmotic pressure. I'll talk about static fluid pressure. I'll talk about Pascal's law. And then lastly, I'll talk about buoyancy. And this material is going to show up on one of the four MCAT sections. That's going to be the Phys Chem section. And hopefully you find this podcast useful. Fluids is a topic that's definitely important for the MCAT, and in my opinion, one of the harder physics topics on the MCAT. So I hope this helps. All right, so as I said in the intro, I'm not really going to talk about moving fluids or fluid dynamics in this podcast. If you want to go listen to that, go skip through about halfway through the cardiovascular system fluids podcast. You can get all of that. So the first thing I wanted to cover in this podcast is some different fluid properties and some topics regarding fluid properties that you might see come up on the MCAT. And I want to start out by talking about what a fluid is. And the easiest way to see what a fluid is to talk about what a fluid is not. So first of all, a fluid is not a phase of matter like a solid, a liquid, or a gas. Although there is a state of matter called the supercritical fluid, which is different than a fluid. It's the phase of matter that is observed above the critical point. So if you look at a pressure temperature diagram, you'll see at very high temperatures and high pressures, you can go above the critical point. And at this point, you become, or I guess the compound that you're looking at becomes a supercritical fluid. And so essentially, when a compound is a supercritical fluid, it's no longer a gas, it's no longer a liquid, it's somewhere in between both of those, which is kind of interesting, kind of cool. But don't confuse supercritical fluid with fluid itself. Supercritical fluid is a state of matter, a fluid is not. What really sets apart a fluid from everything else is that it has the ability to flow, which sounds pretty obvious, but I think there is a more physicsy math definition that I think kind of helps you see this, as well as introduces a few important physics concepts and vocab to know. So I'm going to introduce that definition. A physics professor would say that a fluid is a material that deforms or yields when a shear force is applied. And that's obviously a pretty physicsy definition. You might be saying, huh? So let me break this down a little bit more. So first off, you need to understand what a shear force is. So a shear force is a force that acts parallel to the surface of an object. And this is in direct contrast to a normal force or a normal stress that acts perpendicular or normal to a surface. So think about it this way. Think about how a mom texts, right? I'm assuming this kind of goes the same for all moms. They have their phone and it's like 2 feet away from their face, and they take their index finger and they just tap each and every single letter, and it just looks kind of funny. And so when they're doing that tapping motion, you're bringing your index finger forward and you're hitting your phone. That would be a normal force on your phone, right? You're poking it perpendicularly to the screen. However, let's say your mom's swiping now. Well, swiping would be a shear force that's applied to your phone, right? You're applying that force in a parallel direction to the phone. So you can think about swiping, shear force, poking or tapping the phone would be normal force. So all those two terms have to do with force is the directionality that the force is applied to a surface. And again, what makes a fluid is its ability to move or deform when that shear force is exerted on it. Another way to think of this is as follows, and this is actually the way I learned it in my fluid mechanics class. So imagine you take water and you just place this water between two metal plates and just pretend that for whatever reason this water doesn't just flow away. So you have water, you have it between two metal plates, and say the bottom metal plate is actually drilled to the table, whereas the top plate is free to move. So now as you apply a shear force to this top plate with the water in between it, this top plate is actually going to start to move, right? And it's going to move kind of in a parallel manner away from that bottom plate. And you could, of course, imagine this top plate like sliding on the water. That's not what I want you to imagine. What I want you to imagine is that this water is actually kind of just moving with this top plate. Or in other words, the top layer to this water is moving along with that top plate, whereas the layer very near the bottom plate isn't moving at all. And so you can see that over time, you're going to actually change the shape of this water. And again, for whatever reason, it's not just flowing away, but it's changing its shape as you apply this shear force via this top plate as it slides parallel to the bottom. And I hope that doesn't confuse you more, but that's just kind of how I learned it. And that helps me think about that shear stress and kind of see what that does to a fluid. And so to put it very, very simply, a fluid is something that can flow and change its shape, whereas things that are not fluids cannot. So in general, gases and liquids are fluids, and solids are not fluids. So that's the most basic definition of a fluid. The next thing I want to talk about here is surface tension. And surface tension really only applies to liquids. It doesn't apply to gases because gases don't really form a surface, right? Because they tend to just disperse, around a room. Whenever you have them in a container, they're just going to disperse all around and don't form a surface. So just keep that in mind, that when I talk about surface tension for fluids, I'm talking about liquids. So surface tension is the force required to break the surface of a liquid. And it can be measured a few different ways, one of which is you can measure the force required to break some length of film. And by film, I just mean like the surface of a liquid. And this is typically given in units of millinewtons per meter, or force over length, where the force is the force required to break the film and the length is the length of the film. And that's kind of the physicsy definition. Another way to think about it, and the way that we typically think about it, is that surface tension is just a measure of the cohesive nature of a liquid, i.e. how hard is it to penetrate the surface of that liquid. And this word cohesion brings me to two words which you should be able to differentiate between on the MCAT, that is cohesion and adhesion. So cohesion is the attraction between two of the same fluid molecules. So that's like I have a glass of water, that's the attraction between individual water molecules, which in the case of water is hydrogen bonding. Then when I talk about adhesion, what I'm talking about is the attraction between fluid molecules and some other substance. So as you probably know, water is somewhat attracted to glass. And so if I have a glass of water, you may see some of that water kind of come up on the sides of that glass a little bit, and have this kind of form a little bit of a meniscus. And so that's due to adhesion. So just be able to differentiate between those two terms. But back to surface tension. So as I was saying, surface tension is measured in units of force per length, usually millinewtons per meter. And typically when you have higher surface tension, that means you have stronger intermolecular attractions. So as I was saying, water molecules are able to hydrogen bond with each other, and therefore you have very strong intermolecular attractions, and you have a strong surface tension of pure water, which is around 72 millinewtons per meter. On the other hand, when you have compounds that have lower surface tensions, that's typically because they have weaker intermolecular attractions. You could think of something like hexane, which is just going to have these kind of weak van der Waals, attractions between molecules, and that has a surface tension of 18 millinewtons per meter. And one way you can actually measure surface tension is through what's known as contact angle. And contact angle is actually typically used to measure surface wettability, which is just a measure of how adhesive a surface is. But you can actually use it to measure surface tension, as I was saying. In this experiment, would go something like this. So you take like a sheet of wax paper and you take a drop of whatever liquid you're looking at, let's say water, and you drop a drop onto that sheet of wax paper. Now, in the case of water, you'd see this nice round, thick with like 4 C's drop that forms with a big contact angle. And the contact angle is essentially the angle that forms between the edge of the droplet and the surface of the wax paper. You can go Google an image real fast of contact angle if you're curious and if you can't really picture that in your head. And then let's say that I took this hexane and I dropped a drop of hexane onto this wax paper. Well, it would form a lot more of like this flat drop, kind of sad little drop that's all flat. And that would be because the surface tension of this hexane is a lot lower than that of water, right? Water has a lot more of a cohesive force, and therefore that droplet is kind of going to be more compact and more round, whereas with hexane, a lot less cohesive forces, it's going to be more spread out. And using that contact angle, you could actually use an equation and solve for the surface tension. And don't worry about knowing the equation. It's called Young's equation. You'd probably be given that in a passage if you were ever to use it, which even then I kind of doubt. But the takeaway message here is that high contact angle equals high surface tension, whereas low contact angle equals low surface tension for the same material. Again, we're just talking about wax paper here. All right, so that's a little bit of an intro to surface tension. The next thing I want to talk about here has to do with absorption versus adsorption versus adsorption, and just knowing the difference between these three terms. And I did mention adhesion a little bit earlier, which is the attraction between fluid molecules and some other substance or some other surface. I think I gave the example of water and glass. And similar to adhesion is the concept of absorption. So I just want to be clear here about the difference between absorption, adsorption, and then thirdly, adsorption. All right, so the term adsorption with a D refers to a liquid or a gas, which are fluids, that stick to some surface. So an example here would be like water adsorbing to the glass surface in a graduated cylinder, and you see this meniscus that forms. My brother, who is a chemical engineer at a gas processing plant and is much smarter than I, gave me an example of gas adsorption. What he said he uses is called
MolSieve, MOL, and then SEIVE.
And MolSieve is just an abbreviation for molecular sieve. And essentially this works a lot like chromatography beads. It's these small pellets that have these really, really small openings that allow gas to flow through them, but can actually adsorb certain gases, like, for instance, ionic gases. And so that actually allows you to then purify different types of gases, get rid of carbon dioxide, carbon monoxide, hydrogen sulfide, or any other gases that you don't want in your system that are weakly polar. The next term here to know is absorb with a B, and that is when fluid is taken up by another phase. So for instance, you could have water that is soaked up into a sponge, like a sponge absorbs the water, which is water going into a solid phase, which is a sponge. Or you could have gas that's absorbed into a liquid. So again, absorb is a fluid taken up by another phase. Last but not least is adsorb with a T. And this is not actually a real word. I just made it up. So sorry if you just listened this whole time and were like, what is adsorb? Like, shit, I'm finally going to learn something. But that's not a word. So just all you got to know is absorb and adsorb. All right, so the last thing I want to talk about in this section of the podcast on fluid properties is vapor pressure and Henry's law. So let's start with the definition of vapor pressure, which is a bit of a confusing concept. So the vapor pressure of a liquid is the equilibrium pressure of a vapor above its liquid. And that's a bit confusing, so I like to think about it as the pressure of the vapor that results from the evaporation of a liquid in a closed container. So say I took water and I put it in a water bottle, and now I leave it under the sun at 80 degrees Celsius. Well, eventually pressure is going to build up because there's some evaporation, but it reaches an equilibrium where I have some vapor, some liquid, and some certain pressure, and it's going to be steady and it's going to stay right at that pressure. That's the vapor pressure at that specific temperature. And this brings me to a few important points. The first being that vapor pressure is dependent on a few other variables. So first and most obvious, what I talked about in this example was temperature. So depending on the temperature, the vapor pressure of a specific liquid is going to change. And these two quantities are directly proportional. As I increase the temperature, I increase the vapor pressure. Another factor that determines vapor pressure is the concentration of solutes that are dissolved in that liquid. So for a pure liquid, you don't have to worry about this, but as you add in more solutes, say I'm dissolving salt into water now, you're going to actually decrease the vapor pressure. And this is in a dose-dependent manner, meaning that the more solute I dissolve in a pure liquid, the lower the vapor pressure becomes. And there's actually a well-defined law that describes how the addition of a solute to a pure liquid alters its vapor pressure. This law is called Raoult's law, and it says that the vapor pressure of some liquid is going to be equal to the mole fraction of the solvent times the vapor pressure of the pure solvent itself. In other words, you have a mole fraction multiplied by the pure component vapor pressure. So let's take, for example, a mixture of water and salt. Say I have 1 mole of sodium chloride mixed with 1 mole of water. What is the molar ratio of the solvent in this case? Well, it's just going to be 50%, right? The solvent is water. Half the moles in this mixture of are water, so that's a molar ratio of 50%. And then what would be the vapor pressure of pure water at whatever temperature I'm at in this system? I'd find that number, and now I would multiply the 0.5, that molar fraction, by that pure component vapor pressure, and I would get the vapor pressure for that mixture. And that is Raoult's law. Okay, so that was the second factor that can determine the vapor pressure of a liquid. The third factor is the type of solvent or the type of liquid that I'm looking at. So you can look at the vapor pressures of a bunch of different liquids at one given temperature. You can compare water to hexane, to ethane, to methane, to all these different liquids, and you'll see that they all have different vapor pressures. And that's just due to the intrinsic properties of that specific liquid. Water has a pretty high vapor pressure because, as I said earlier, water can have these really strong intermolecular attractions known as hydrogen bonds, and therefore doesn't really want to come out of solution and go up into vapor form into a gas. But some liquids have a really intrinsically low vapor pressure, like methane. So those are 3 things that the vapor pressure depends upon. And notice what it does not depend on. It doesn't depend upon the surface area of the container you're looking at, right? You think if you have a big old bucket of water versus like a test tube, maybe the vapor pressure is going to be different. They're going to be evaporating at different rates, etc. And you would be right about one thing. You would be right that the water in that big bucket is going to evaporate faster than that in the little test tube. But the vapor pressure is an intrinsic property of the liquid itself. It doesn't have to do with the container you have it in or anything else like that. And the last thing I should mention here is that there's a relationship between the boiling point of a liquid and the liquid's vapor pressure. And the relationship is that the boiling point of a liquid is when its vapor pressure is equal to atmospheric pressure. So essentially what you're doing when you're boiling a liquid is you are heating it up, and what that's doing is that is increasing the vapor pressure. So as you heat up this liquid, its vapor pressure is going to keep going up until, boom, you start boiling that liquid, and that's the point at which its vapor pressure equals atmospheric pressure. And similar to Raoult's law, which again looks at how vapor pressure changes when you add a solute to a liquid is what's called Henry's law, and that looks at the dissolution of gas into a liquid. And one of the classic examples of gases dissolving in liquid is that of sparkling water, which is carbon dioxide dissolved in water. And so what Mr. Henry Cavill's law says is that the amount of dissolved gas in a liquid is proportional to its partial pressure above that liquid. In terms of a mathematical equation, Henry's law says that the solubility of a particular gas is equal to Henry's constant times the partial pressure of that gas. In other words, as the partial pressure of some gas goes up above a liquid, the more of that gas is going to be dissolved in that liquid. And the last thing I'll say here is that this Henry's constant is just essentially the proportionality factor. So it depends upon what type of liquid you're looking at, what type of gas you're looking at. It depends upon temperature. Depends upon a bunch of different things. But really what I'd keep in mind here is the fact that when I'm dissolving a gas in a liquid, if I raise the pressure, I dissolve more of that gas in the liquid. So says Henry's law. All right, in the next part of this podcast, I want to get into more of the physics topics related to fluids, particularly that of static fluid pressure. So I'm going to talk about Pascal's law. I'm going to talk about gauge pressure versus absolute pressure. I'm going to talk about osmotic pressure. And lastly, I'm going to talk about one of the harder to understand concepts, in my opinion, and also probably the hardest to spell, and that's buoyancy. So let's first start with static fluid pressure in general. And again, a static fluid is just one that's not moving. So something like a swimming pool or a water tank or a glass of water, any of those is an example of a static fluid. And you'll know that static fluids can indeed exhibit pressure if you've ever been in a pool. You know that the deeper you swim, the more pressure you feel, especially like on your head and your ears will pop and your eyes start to hurt as you swim deeper and deeper. You know, I remember swimming in the deep end as a little kid and you try to swim down till it hurt and then you go back up. And that's actually due to the pressure of all that water above you. And that, I think, is the most important thing to understand about static fluid pressure, is that it's just due to how much water is above you, or how much fluid is above you. In the case of a swimming pool, it's how much water is above you. And so that simplifies down into the following equation, that static fluid pressure is equal to density times gravity times the height of the fluid that is above you. And you may have heard this equation as pressure is equal to rho GH, where rho is density. And so really this equation kind of breaks down to one variable, and that's the height of the fluid above you. Because fluid density, which again is rho, is pretty constant in a lot of systems in which you're going to be using this equation, right? It's usually going to be water, and if it's not water, it's going to be something that's pretty similar to water, say blood, or I don't know, what's another physiological fluid? Plasma. All of that really has a density close to water. You know, you're typically not like taking a bath in mercury or something that's got a really high density. So that's pretty much constant, fluid density. Gravitational constant is by definition constant. So the one thing that's changing in a lot of these calculations that you're going to be doing is the height of the fluid. And to illustrate what I mean by the height of the fluid above you, it might be a bit confusing. Take this example. So say you're swimming in a pool and you're swimming 2 feet under the surface of the water. Well, you're going to be experiencing pressure from that 2 feet of water. Let's say you swim down 2 more feet into the water. You're going to be now 4 feet under the water. So there's going to be 4 feet of water above you. And during this maneuver from 2 feet underwater to 4 feet, the pressure increased by 2 times because you're doubling the height of the water above you. So again, this pressure is equal to rho GH is one of those equations that you really have to have memorized, I think, for the Mcat. So that's really important to understand and know how to apply. So do some practice problems if you're not too familiar with that equation. But one last thing I want to say here is notice what this equation does not depend upon. It doesn't depend upon fluid shape, the fluid mass, the fluid surface area, a lot of other factors that you may think matters. So in other words, if I were to put you in a giant Olympic-sized pool and you were to swim 2 feet under the pool, your pressure would be, let's say 10. I'm just making that number up, but just pretend it's 10. Now, let's say I pick you up and I put you in like a kiddie pool that's deep enough for you to swim 2 feet down. Now, the pressure on you in both cases is going to be exactly the same, even though in one case you're in an Olympic-sized pool, and in the other case you're in a kiddie pool. It's the same. It just depends upon how much water is above you. It has nothing to do with how big the pool is, the shape of the pool, anything else like that. All right, so that's kind of the basis for static fluid pressure.
Thanks for checking out the Prospective Doctor MCAT Basics podcast. Sam's doing a killer job taking you through the most important MCAT topics, but what if you need a little extra help? How does a 5, 10, or even 15-point increase in your score sound? Imagine how your chances of admission could increase. Med School Coach's Mcat Tutoring can get you there. With the most rigorous selection process of any tutoring company, we see amazing results. We deconstruct each student, find a plan that is going to work, and help execute it. That's why our students add an average 12 points to their score. Completely physician-run and operated, and focusing on nothing but medicine. It's no wonder over 10,000 past students have trusted Med School Coach to get them through the MCAT and into medical school. Check out medschoolcoach.com today and mention code PODCAST for 5% off.
The next thing I want to talk about here is an application of static fluid pressure that's called Pascal's law. So Pascal's law starts on the basis, and this is what you got to pay attention to. This is interesting. Starts on the basis that pressure applied to a fluid is evenly distributed throughout the whole fluid. And this is kind of counterintuitive, right? Think about, again, an example of a pool. If I belly flop into the deep end of a pool, to me what's intuitive is that only the local area where I belly flop is going to feel the pressure of that belly flop. Well, instead, what Pascal says is that the whole pool is going to feel the pressure that I've just applied from that belly flop. Pascal's law forms the basis for fluid hydraulics. And what I want to do here is I want to describe a system and then get into some of the mathematics in the system and just kind of help you see how hydraulics works, as well as introduce some equations that you might see come up on the MCAT. So what I want you to imagine is a system where I have a tube that is shaped like a U. And the openings on each side of this tube are different. And it's a pretty big tube, maybe 10 feet in total. Imagine it being the height of a person, but in the shape of a U. So again, each side of this pipe has different sized openings. One side is really thin and skinny. The other side is pretty large, big diameter. Okay, so now imagine I take water and I just fill up this tube. Next, I'll take 2 paddles, or like the plungers of a piston, if you've seen what those look like, and I will insert these into each side of this U pipe. And again, these paddles will be different sizes because the different sides of this U tube have different sized openings. And these are going to sit in there very flush with the pipe. All right, so that's the system you have in front of you. Let's talk more about the physics of it. So if you think back to really basic physics, what is force equal to? Force is just equal to pressure times area. And what do we know about a fluid? We know that in a fluid, the pressure is going to be constant all the time. And that's what Pascal's principle says, or Pascal's law. So we know that since pressure is constant, I'm just going to divide area over to the other side. We know that force over area is going to be constant when that force is applied to a fluid. So what does this mean for our system? Well, this means that if I press down on one of the paddles, I increase the pressure in the fluid, and that pressure is going to be felt throughout the fluid, which is then going to apply some pressure to the other paddle. In other words, this equation that I have where force over area is equal to some constant, which is going to be just the pressure of that fluid, that's going to be true for both sides of this U tube. For each paddle, force over area is equal to the same constant. So what I can do is I can set force over area of paddle 1 equal to force over area of paddle 2. And of course, these forces are going to be in opposite directions. So if I press down on paddle 1, paddle 2 is going to feel the force upwards. And think about what this allows me to do. So this allows me to apply a small force to a small area and get out a very big force to a big area. So if this U tube was big enough, let's just say that the area on one side was like the size of my finger, and the area on the other side was the size of like a large car. Let's just say, for example, well, if I was to put that car on the other side of the YouTube and press down with my finger really hard, I might actually be able to lift that car. And mathematically, that's just due to the fact that force over area of plate 1 has to equal force over area of plate 2. If this concept isn't really making sense or is just hard to visualize, which I'm guessing it is, you can go on YouTube and type in Pascal's law hydraulics. And one of the first videos is one that's done by the organic chemistry tutor. It's great. I think it's very visual and help you learn this if you're struggling to do so. So in terms of Pascal's law, I think there's 2 takeaways. Number 1, that when you apply pressure to a fluid, that pressure is evenly distributed throughout the entire fluid. And number 2, I would memorize that equation that the force over area of plate 1 is going to be equal to the force over area of plate 2 in a simple hydraulic lift system. So that's Pascal's law. Before I go on to osmotic pressure, I want to quickly touch on the difference between gauge pressure and absolute pressure. So it's a pretty simple concept, but I think it's a concept that can kind of trip people up. So let's imagine here that we're talking about the pressure in a big water tank. So the absolute pressure would be the pressure in reference to a perfect vacuum, like somewhere there's literally zero pressure, somewhere like space. So in terms of the water tank, this would be like me measuring the pressure of the water tank in reference to the pressure of space. So what I have to do here is I'd have to first find the atmospheric pressure, and then I would add that to the hydrostatic pressure, which again would just be the height of the fluid in that tank. On the other hand, gauge pressure is pressure in reference to atmospheric pressure. In other words, if I was to measure the gauge pressure in the tank, all I would do is I would look at the hydrostatic pressure. I'd say, okay, I have X height of water in the tank. Here's my pressure at the bottom of the tank. I would not include atmospheric pressure because atmospheric pressure would be the 0 point of the scale for gauge pressure. So overall, the easiest way for me to remember this is when I hear absolute pressure, I think, okay, pressure in reference to space, so I need to include atmospheric pressure. Then I hear gauge pressure, I think, okay, this is pressure with reference to the atmosphere, so I don't need to include the atmosphere because that's the 0 point in this scale. And if that's not clear enough, take this example. So say you're going to your primary care physician and you get measured and your primary care physician says, your gauge height is 2 inches. And you say, what are you talking about? My gauge height is 2 inches. And your primary physician says, yeah, it's what we're using now. Your gauge height is just your height in reference to the average male. And the average male is 5'9". So you say, okay, 5'9" plus 2 inches. That makes me 5'11". And so that 5'11" would be your absolute height. Your gauge height would be 2 inches since gauge height is in reference to the average male height. All right, the next thing I want to talk about here is osmotic pressure. And this is a topic that I've seen definitely come up on the MCAT, so this is an important one. And you need to have a conceptual understanding of osmotic pressure and why it exists, as well as a mathematical and physiological understanding. So I'm going to go through all 3 of these things in this next section. Number 1. Let's start with the conceptual understanding of osmotic pressure first. This textbook called Quantitative Human Physiology defines osmotic pressure as the pressure that must be applied to the solution side to stop fluid movement when a semi-permeable membrane separates a solution from pure water. And to me, this definition is a little bit, So let's dig into that a little bit more and break this down a little further. So imagine I have a container with 2 compartments. Each of these compartments are separated by a semi-permeable membrane. And a semi-permeable membrane is just a membrane that only allows water to flow through it, but nothing else. No ions, no small molecules, nothing, just water. And so what I do is I pour pure water into one compartment of this container, and I pour tap water, which has some concentration of ions and some concentration of particulate matter, sometimes gasoline, depending on where you live. And you observe an interesting phenomena that occurs once you have these 2 different liquids on different compartments of the same container separated by a semi-permeable membrane. What happens is that some of the pure water will flow across the semi-permeable membrane into the compartment that holds the tap water, which again has ions and particulate matter floating around in it. And if you let this sit for, 10, 15 minutes, it will come to equilibrium and you'll have more fluid than you started with in the tap water compartment and less in the pure water compartment. And essentially what we did is we turned pure water into tap water. Shout out Jesus. But this movement of pure water across a semi-permeable membrane into a compartment that contains water with ions and other particulate matter is really due to concentration gradients and molecules flowing down their concentration gradient. And it has to do particularly with water molecules moving down their concentration gradient. And just a quick aside, we typically don't think about water moving down its concentration gradient. We think about stuff in water moving down its concentration gradient, like say glucose, moving from the cytoplasm into cells because it's high in the blood. You just ate a big meal and now it's moving into the cells and it's just moving down its concentration gradient. But in the case that I just talked about with the semi-permeable membrane, water is the molecule that can move in this system and therefore it flows down its concentration gradient. And so think about where the water wants to flow in this system that I have. The water wants to flow into the tap side because it wants to even out the concentrations on both sides of this semi-permeable membrane. But that's technically impossible, right? Because there's no particulates in this pure water. There's a bunch of particulates and ions and stuff in the tap water. And so, yes, a bunch of water can flow over and start to decrease the concentration on the tap side, but it's never going to be zero, which is what it is in the pure water. So what happens? You don't have all the water move over to one compartment and then there's nothing left in the other. That doesn't happen. It just stops at one point, right? It reaches equilibrium where some of the water moves over, but not all of it. And why is that? Why does not all the water move over to the tap side to try to, lower the concentration and fulfill that concentration gradient? Well, the reason that this pure water doesn't just fully flow into the tap side is because there is another pressure that's acting on the fluid, and that's going to be gravity. Think about the height of the water in this situation. As some of this pure water moves over to the tap water side, the height of the tap water side is going to get bigger and bigger, and we know that hydrostatic pressure is equal to the height of the fluid. So we know the hydrostatic pressure on one side is going to be greater than the other. And so this pressure is actually going to drive back against the concentration gradient. And I should mention here that the pressure on both sides is not going to necessarily be the same because you have this semi-permeable membrane that's separating both. So Pascal's law doesn't apply in this situation. So what happens is that eventually, right, you get no net flow of pure water into the tap water side, and it just stops, right, with a little bit more water in the tap water side, a little less in the pure water side. And that is when the hydrostatic pressure that's pushing back against the concentration gradient perfectly matches that of the driving force forward of the concentration gradient. So if we were to zoom in on the semi-permeable membrane, you'd have this concentration gradient pulling the pure water through the membrane, and then you'd have this pressure from the force of gravity on the fluid that's kind of pushing that pure water back through the membrane the other way. And once those forces are equal, then there's no net movement of pure water through the membrane. And so let's go back to this definition. Again, osmotic pressure is the pressure that must be applied to the solution side to stop fluid movement when a semi-permeable membrane separates a solution from pure water. So in this case that I've just presented, the pressure that must be applied is just that of gravity. And so in this case, the gravitational pressure, or the gravitational force that's exerted on this fluid is equal to the osmotic pressure. Another way I could have done this is I could have put the same paddle or plunger over the solution side, again, which is tap water, and I could have applied a force myself and increased the pressure in that fluid, and then I could have prevented any movement of pure water over to the tap water side by just applying this pressure. And what would that pressure be equal to? Well, that would be osmotic pressure, which would be equal to the pressure from the force that gravity exerts in the before example. More simply put, osmotic pressure is essentially the pressure needed to counteract the concentration gradient of water. That's kind of the most simple definition of osmotic pressure. So that's the basic concept behind osmotic pressure. Number 2. As I mentioned, the second understanding you need to have here in terms of osmotic pressure is a mathematical understanding. And so there's an equation that describes osmotic pressure. It's called Van Hoff's law. And it says that osmotic pressure is equal to the Van Hoff Index times the molar concentration times the gas constant R times temperature T in Kelvin. And so you may see this equation as pi, which is the symbol for osmotic pressure, is equal to ICRT. And as with all equations on the MCAT, I think the most important thing to understand here are the relationships between osmotic pressure and the different variables in this equation. For example, temperature is directly proportional to osmotic pressure. So if I increase the temperature of a solution, I increase its osmotic pressure. Next, the Van Hoff Index, which is I, also plays a role in determining osmotic pressure. For non-ionic compounds, the Van Hoff Index is 1. But for ionic compounds, the Van Hoff Index is equal to the number of discrete ions that are produced upon dissolution of a specific solid or compound. So for instance, take sodium chloride, which is NaCl, that dissolves into sodium and chloride, which is 2 ions, so that has a Van Hoff Index of 2. Take sodium sulfate, which is Na2SO4, that breaks up into 3 molecules once it dissolves, right? 2 sodium and then 1 sulfate. And so that has a Van Hoff Index of 3. In practice, what this means is that if I'm comparing the osmotic pressure of a solution that has a bunch of salt compared to a solution that has a bunch of proteins and organic molecules, and these are the same concentration, then the solution with salt is going to have a higher osmotic pressure because it's going to break up into a bunch of different ions, and that Van Hoff Index is going to be greater. And that's, again, if I'm comparing 2 solutions with the same overall concentration. And then lastly, the osmotic pressure is proportional to the concentration of a solution. In other words, if I have pure water and I'm dumping in sodium chloride, the more sodium chloride I add to that solution, the higher the concentration gets, and also the higher the osmotic pressure gets for that particular solution. So keep that in mind. The more things I add to the solution, the higher the osmotic pressure gets, and that makes sense. Number 3. So the last context that I think it's important to understand osmotic pressure in is in the context of physiology. So when a physician wants to talk about the concentration of someone's plasma, they typically will report it either as osmolarity or osmolality. And what osmolarity is a measure of all the solutes in the blood at a given time per fluid volume, and that's usually in milliosmoles per liter. On the other hand, plasma osmolality is a measure of all the solutes in the blood at a given time per mass, and that's usually given in milliosmoles per kilogram. And human plasma is typically right around 300 milliosmoles per kilogram. In other words, you have about 0.3 moles of solute per kilogram of plasma. And if you use Avogadro's number to convert that to number of particles, remember that's 6.022 times 10 to the 23rd, that is going to be 1.8 times 10 to the 23rd particles per kilogram of plasma, which is a lot. It seems like too much, but also a kilogram of plasma is a lot. So you've got a lot of particles floating around in your plasma. But anyways, the takeaway here is know the difference between plasma osmolarity, plasma osmolality. I would try to remember that 300 milliosmoles per kilogram is what human plasma is around. And then the last thing I'd understand here is the difference between hypertonic, hypotonic, and isotonic solutions. And I'm going to introduce these 3 terms in the context of cells in the plasma. And for this, I'm assuming that these cells have an osmolality around 300 milliosmoles per kilogram. So the first thing I got to say is when we're talking about hypertonic, hypotonic, isotonic, you're comparing 2 different solutions or two different things. So in this case, I'm going to compare a cell to the solution I'm placing it in. So let's start with hypotonic. So a hypotonic solution is a solution that has an osmolality below the cell. So this would have an osmolality of, say, 250 milliosmoles per kilogram. And what's going to happen when I place that cell in a hypotonic solution is that it's going to cause that cell to burst because the cell is going to fill up with water to try to even out those concentration gradients, right? Because the cell is actually more concentrated than the solution that's surrounding it. And so to try to even that out, water is going to move into the cell, which is going to dilute the inside of that cell to try to get to the same solution as the solution that's on the exterior of that cell. It's going to cause the cell to burst. And I always try to remember hypotonic bursting cells because of that O, right? You see the O and you think, oh, it's going to make that cell get all round and burst. Hypotonic. Hypertonic, on the other hand, is if I were to take that cell and place it in a solution that has an osmolality way above its own osmolality. So say that I take that cell and I place it in a solution that has an osmolality of 325 milliosmoles per kilogram. What that's going to cause the cell to do is shrivel up as water moves from the cell to the exterior as it tries to even out that concentration gradient. So hypertonic solutions cause cells to shrivel up. And then lastly, I could place the cell in an isotonic solution. That's just going to be a solution that has the same osmolality as the cell itself, or has an osmolality around 300 milliosmoles per kilogram. And in this case, the cells would be happy, right? There's no net movement of water into or out of the cell. It's going to stay the same size. It's just going to be really comfortable. All right, so that's some things that you should know about osmotic pressure. Again, I went through a conceptual understanding of osmotic pressure. I went through a mathematical understanding of osmotic pressure. And I would know that equation. I think that's important to know for the MCAT. And then lastly, I talked about it in terms of physiology, specifically that of cells. The last thing I want to talk about in this section of the podcast is buoyancy. I'll talk about the buoyant force. I'll talk about Archimedes Principle. And then I'll talk about floating objects versus submerged objects versus sunk objects. As you probably know, when you throw somebody in a pool, younger siblings, whatever it may be, they typically float, or at least they float for a little bit. And why is that? Well, that's due to what's known as the buoyant force. And since this buoyant force is a force, it is a vector quantity, meaning that it has both magnitude and direction. And in terms of the net buoyant force that an object feels when it's in water, it has a directionality of up, right? The direction is always opposing gravity because it makes you float, right? It is opposing gravity. And the magnitude of this buoyant force depends upon a few different things. And this is where I get into what's known as Archimedes Principle. And Archimedes Principle states that the buoyant force is equal to the mass of fluid that is displaced by a floating or submerged object. And so the equation that you can then derive is that the buoyant force is equal to the density of the fluid times gravitational constant times the volume of the fluid displaced. And so obviously by that equation, you can see that the buoyant force depends upon how dense the fluid is. The more dense the fluid is, the more of a buoyant force you'll feel, i.e. if you threw your sibling into a pool of mercury, they would float right on the surface because the density is so high. And then obviously the more fluid that's displaced by that object, the higher the buoyant force is going to be. And so I think there's 3 unique cases that you can apply this equation to and that you should understand for the MCAT. That is the case of a floating object, the case of a submerged object, and the case of a sunk object. So first, for a floating object, the buoyant force has to be equal to the weight of that object, right? If the weight of the object is greater than the buoyant force, then that object is going to sink. So for a floating object, that's kind of the thing to remember. Buoyant force equal to the weight. And I'm not going to prove this, but mathematically speaking, in the case of a floating object, the density of the fluid is greater than the density of the object. The next case is a submerged object. And this is an object that's fully under the water, but it's not sunk to the bottom. An example would be like a water balloon. If I placed a water balloon in water, it's going to be submerged. It's not going to sink. It's not going to float. It's just going to be submerged. And like a floating object, the buoyant force is equal to the weight of the object. The thing here that's a little bit different is that you can say that the volume of fluid displaced by this object is just equal to the volume of the object, right? Because it's displacing its own volume because it's submerged in the water. I hope that makes sense. And lastly, you can say in this case that the density of the fluid is equal to the density of the object if that object is submerged. All right, the last and final case here is that of a sunk object. So this would be like dropping a penny in a cup of water, right? It just shoots straight to the bottom. And in this case, the weight of the object is actually greater than the buoyant force. The buoyant force isn't great enough to hold up that object, and it just drops to the bottom of whatever container full of liquid you have. And again, in this case, you can say that the volume of fluid displaced is equal to the volume of the object. And in terms of density, when an object sinks, you can say that the object's density is greater than the density of whatever fluid that you're putting it in. All right, the last thing I want to talk about buoyancy and also in this podcast is what's called apparent weight. So you may have noticed that when you have an object underwater, it seems to weigh less. If you were to take a bench press and put it at the bottom of a pool, you notice you could probably bench a lot more. And this is because the buoyant force basically does some of the lifting for you. The buoyant force is going to be an upward force that essentially cancels out some of the weight of that object when it's submerged. And I have seen it come up on some of the practice material where the MCAT asks you, what is the apparent weight of this object that's fully submerged? And what they're really asking is, if I placed a scale at the bottom of this pool and then put this object on that scale, what would it weigh? And you can use the following equation to do this. You could go look up a derivation of this equation if you want to understand it better. I just put this equation on a note card and just kind of memorized it. This equation is that the density of an object over the density of a fluid that it's in is equal to the weight of that object divided by the weight of that object minus its apparent weight. And then if you want to solve for the apparent weight, you can just plug in what you have and solve for that apparent weight. Again, that equation is the density of an object divided by the density of whatever fluid it's in is equal to the object's weight divided by, and this whole next term is all in the denominator, divided by weight of the object minus its apparent weight. All right, so that concludes the Fluids podcast. Again, this podcast was more geared towards statics. I have another podcast that I combined with the cardiovascular system that deals a lot more with moving fluids. So if you're interested, skip through about halfway. Let me look real fast where it's at. Skip forward to 43 minutes. So at 43 minutes, I talk about moving fluids, and I talk for about 20 minutes about that. But I think in general, fluids is a really important topic for the MCAT. So if you need to listen to those podcasts multiple times, do it. I know each of them is very heavy on the details. As always, thanks for listening. If you like this podcast, go give us a review rating on iTunes. Helps us reach more students. I like seeing them as well. Good luck as you get ready to take the MCAT.
Thanks for listening to Prospective Doctor's MCAT podcast. If you're a pre-med, you'll want to check out prospectivedoctor.com for tons of free tools, articles, and more podcasts that cover your pre-med life. And if you need help on the MCAT or getting